In the early 20th century, astronomers studying faint, dim stars noticed something that did not fit with existing models of dying stars. These objects were small, extremely dense, and stayed warm far longer than expected. Telescopes showed that their light faded very slowly. Decades of observation revealed a strange pattern. The smaller and denser these stars were, the more persistently they held their heat. This behavior repeated across different regions of the galaxy and across different observing teams. At first, this seemed like a measuring error. Instruments were recalibrated. Star catalogs were revised. Yet, the same pattern remained. Dense, compact stars cooled much more slowly than classical physics predicted. This was the first strong hint that a different kind of internal support was at work inside these objects. The answer lies in a physical principle discovered in quantum physics. Inside these stars, matter is packed so tightly that electrons cannot move freely as they do in normal atoms. Electrons are forced into a state where they resist being squeezed any further. This resistance creates a powerful internal pressure. Scientists call this phenomenon electron degeneracy pressure. In simple terms, it means that the building blocks of matter form a solid-like barrier against further collapse, even without heat or nuclear burning. The structure of these stars becomes similar to a giant crystal made of compressed atoms. The normal source of energy that powers active stars, nuclear fusion, has already stopped. There is no new fuel burning in the core. What remains is stored heat locked inside an extremely dense structure. This heat leaks out slowly over billions to trillions of years. A useful everyday comparison is a thick stone oven. After the fire goes out, the stone walls stay warm for a long time. A thin metal pan cools quickly, but a massive brick oven keeps its warmth through the night. White dwarfs behave in a similar way, but on a cosmic scale. Their extreme density acts like a thermal battery, releasing heat at a slow, steady rate. This dense structure traps the heat, preventing energy from efficiently radiating away. The discovery of this behavior changed how scientists understood the final stages of stellar evolution. These stars do not fight death. They are simply built in a way that makes cooling an extremely slow process. What appears to be refusal is actually the consequence of quantum-level structure governing macroscopic objects. At the scale of the galaxy, these stars act as long-lasting embers, quietly marking the passage of time across the universe. A white dwarf does not collapse in the way most objects do because of a balance between two opposing forces deep inside its structure. One force constantly tries to compress the star inward. This force is gravity, the same natural pull that makes objects fall to the ground on Earth and keeps planets moving around the Sunday. The opposing force comes from the behavior of tiny particles called electrons. In everyday matter, electrons move freely around atoms. In a white dwarf, the pressure is so extreme that atoms are squeezed almost completely flat. Electrons are pushed into very limited space. When this happens, the electrons create a powerful resistance simply by existing in a confined state. This phenomenon is known as electron degeneracy pressure. In simple language, it means that matter cannot be compressed beyond a certain point because the particles refuse to share the same space. The internal structure of a white dwarf becomes a densely packed lattice of atomic nuclei surrounded by trapped electrons. The entire star functions like one solid object rather than a ball of gas. This structure makes further collapse nearly impossible unless the star gains additional mass from outside sources. A familiar example can be seen in a tightly packed suitcase. A half-empty suitcase can be compressed easily by pushing on it. A suitcase packed full of hard objects cannot be squeezed smaller, no matter how much force is applied. The objects inside block any further compression. A white dwarf behaves like an overloaded suitcase, but with gravity pushing from all directions at once. Natural phenomena around white dwarfs also reflect this balance. Their surface gravity is extremely strong, yet their size remains stable for billions of years. They do not produce light through burning fuel. Instead, their visible light comes only from leftover heat slowly escaping. Historical observations confirmed this internal support mechanism when astronomers compared the mass and size of these stars. Heavier white dwarfs were found to be smaller, not larger. This counterintuitive pattern showed that a new type of physics was controlling their structure. The final picture revealed a star that survives not by fighting gravity, but by being held up by the natural limits of how tightly matter can be compressed. On a cosmic scale, this balance allows white dwarfs to exist as stable, long-lasting remnants long after their original stars have stopped producing energy. When a white dwarf is formed, it begins a long process of slow change that lasts far beyond the lifetime of ordinary stars. This process is not driven by burning fuel. Instead, it is controlled by how slowly stored heat escapes from an extremely dense interior. The lifetime of these stars can be understood by looking at their structure. A white dwarf contains a mass similar to the Sun, compressed into a volume close to the size of Earth. This enormous density allows the star to store an immense amount of thermal energy. There is no fresh energy production inside. What remains is residual heat that leaks outward over time. Scientists study this long survival by examining cooling curve. A cooling curve is a chart that shows how the temperature of a star decreases with time. In simple terms, it works like watching a hot drink slowly become lukewarm. A small cup cools quickly. A large insulated container stays warm for much longer. White dwarfs behave like a cosmic version of a highly insulated container. A common everyday example is a large pot of water compared to a small cup. A small cup of hot water loses heat quickly in open air. A large, heavy pot takes much longer to cool, even if both start at the same temperature. The mass and thickness of the material determine how long the heat remains. White dwarfs follow the same principle, but over billions to trillions of years. Natural phenomena linked to this slow cooling include gradual changes in brightness. These stars slowly dim as their temperature decreases, but they never stop existing. They simply become colder and darker over immense timescales. Historically, this idea was confirmed by comparing white dwarfs in star clusters of different ages. Older clusters contained cooler, dimmer white dwarfs. Younger clusters contained warmer, brighter ones. This pattern allowed scientists to use white dwarfs as natural clocks to estimate the ages of star systems. At the scale of the universe, these stars persist long after massive stars explode and smaller stars fade. Their survival time stretches into a future where normal stellar activity has largely ended. This makes them some of the most persistent physical objects in the cosmos. Inside a white dwarf, the source of visible light is not fire, and it is not active burning. It comes from energy that was trapped during the final moments of the original star's life. This remaining energy is called residual thermal energy. In simple terms, it is leftover heat stored inside a dense object before becoming a white dwarf. The original star spent most of its life converting hydrogen into helium through a process called nuclear fusion. Nuclear fusion means small atoms are pressed together to form larger atoms, releasing energy as light and heat. When the fuel runs out, this process stops completely. However, the star does not instantly become cold. The heat, already created, stays locked inside. The structure of a white dwarf allows this stored heat to escape very slowly. Its matter is arranged in an ultra-dense state. Atoms are so close together that heat cannot move quickly through the material. This slow movement of heat is similar to how thick walls in a building slow down temperature changes between inside and outside. A useful, everyday example is a heated concrete floor. When a room with a concrete floor is warm, the concrete absorbs heat. Even after the heater turns off, the floor stays warm for hours. The heat is not being created anymore. It is simply being released slowly. A white dwarf behaves in the same way, but with far greater density and over cosmic timescales. Astronomers confirmed this hidden energy source by observing that these stars show no chemical signatures of active fusion. Their light matches the pattern of a cooling solid rather than a burning gas. This discovery corrected earlier assumptions that faint stars were still weakly burning. Natural phenomena connected to this stored energy include a gradual shift in color. As the surface cools, the light changes from white to yellow, then red, and eventually into invisible infrared. This fading does not require new energy. It is simply the slow release of what was already there. Across the scale of the galaxy, white dwarfs act as archives of past stellar energy. They do not create new power. They quietly emit the last warmth of stars that stopped burning long ago. The ability of a star to fully die is controlled by a strict physical limit linked to how much mass is packed into a small space. White dwarfs exist very close to this boundary. This boundary is known as the Chandrasekhar limit, named after the scientist who calculated it in the 20th century. In simple terms, this limit represents the maximum weight that a white dwarf can support before it collapses further. If the mass stays below this threshold, the internal pressure created by tightly packed electrons can hold the star up. If the mass goes beyond this point, that pressure is no longer strong enough. Gravity wins, and the object collapses into a much denser state or explodes. The internal structure of a white dwarf is built around this delicate balance. Gravity compresses inward, while quantum pressure resists outward. This balance is stable only within a narrow range of mass. A white dwarf is safe only as long as it remains under the critical mass. A useful everyday comparison is loading a bridge with weight. A bridge can hold cars, trucks, and traffic up to its design limit. Once that limit is exceeded, the structure fails. The bridge does not choose to fail. It simply cannot support additional weight. A white dwarf behaves the same way. Its structure works perfectly until nature pushes it past its designed boundary. Natural phenomena connected to this limit include sudden stellar explosions called Type Ia supernovae. These occur when a white dwarf in a binary system steals gas from a nearby star and gains too much mass. Once the limit is crossed, collapse and explosion happen rapidly. Historically, this idea changed the way astronomers classified dead stars. Observations of star remnants made it clear that not all stellar deaths were the same. Some stars stopped as white dwarfs. Others collapsed into neutron stars or black holes. The dividing line between these outcomes was set by math. On the scale of the universe, this mass limit acts like a law that controls the architecture of stellar remnants. It decides which stars fade quietly and which ones end in catastrophic change, shaping the chemical and structural evolution of galaxies over billions of years. Deep inside a white dwarf, the main force that prevents total collapse is not heat and not chemical energy. It comes from the behavior of electrons under extreme compression. This force is known as electron degeneracy pressure. Electrons normally move freely around atomic nuclei. In everyday materials like air, water, or metal, there is plenty of empty space between atoms. In a white dwarf, gravity has crushed the matter so tightly that atoms are pressed almost completely together. Electrons are forced into a very small space. At this density, they can no longer behave like a flexible, moving cloud of particles. The key structure inside the star becomes a lattice of atomic nuclei immersed in a sea of trapped electrons. These electrons generate pressure simply by existing in a confined state. This is not caused by temperature. It comes from a fundamental rule of quantum physics that prevents identical particles from sharing the same exact space and motion. In simple terms, nature imposes a limit on how tightly electrons can be packed. A familiar everyday comparison can be found in a crowded elevator. When a few people stand inside, they can move freely. As more people enter, movement becomes difficult. Once the elevator is completely full, no one can be squeezed in further, no matter how much force is applied from the outside. The resistance is not emotional or voluntary. It is a physical limit created by lack of space. Electron degeneracy pressure works in the same way, but at the level of subatomic particles. Natural phenomena around this structure include extremely strong surface gravity and small physical size compared to normal stars. A white dwarf can contain the mass of the Sun in a body roughly the size of Earth. This is only possible because of the internal support created by compressed electrons. The historical discovery of this mechanism came from combining stellar observations with newly developed quantum theories in the early 20th century. Astronomers observed star remnants that should have collapsed under classical physics. Physicists provided the missing explanation by describing how particles behave when forced into ultra-dense states. On a cosmic scale, electron degeneracy pressure allows white dwarfs to exist for immense spans of time. It acts as a natural structural law that shapes how matter behaves when pushed to the limits of density in the universe. As white dwarfs age, their internal structure slowly changes in a way that does not happen in ordinary stars. Over long periods of cooling, their matter begins to shift from a fluid-like state into a solid, crystal-like structure. Scientists describe this process as crystallization. Inside a young white dwarf, the interior behaves like an extremely dense fluid. Atomic nuclei move slowly through a sea of trapped electrons. As the star loses heat, movement becomes more restricted. Eventually, the nuclei begin to lock into fixed positions, forming an organized lattice. This transforms the star into something closer to a giant cosmic crystal than a ball of hot gas. In simple sense, crystallization means that particles stop moving freely and arrange themselves in a repeating pattern. This is the same general process that occurs when liquid water turns into solid ice. Water molecules in a lake move freely when warm. As the temperature drops, the molecules organize into a rigid structure. White dwarfs follow a similar physical rule, but under far more extreme pressure and temperature conditions. A familiar everyday example can be seen in cooling candle wax. When wax is hot, it flows easily. As it cools, it becomes thicker and eventually solid. The material does not disappear. It simply changes internal structure. White dwarfs experience this same type of transition, but on a stellar scale. Natural phenomena tied to this crystallization include subtle releases of energy. As the internal material reorganizes, small amounts of heat are released. This slightly slows the cooling process and allows these stars to remain visible longer than expected. The idea of crystallized stellar cores was first confirmed by observing variations in brightness of ancient white dwarfs. Astronomers noticed that certain white dwarfs stayed warmer than theoretical models predicted. This discrepancy led scientists to investigate the internal structure and confirm the presence of crystal-like cores. At the scale of the galaxy, this process means that some of the oldest stars in existence are not just faint, they are slowly freezing into solid structures. These objects act as long-lasting records of matter behavior under extreme cosmic conditions. Inside a white dwarf, two powerful forces remain in constant tension. One force pulls inward, the other resists collapse. This silent struggle defines the physical nature of these stellar remnants. Gravity is the inward force. It acts on every particle of mass, compressing the star toward its center. The more mass packed into the star, the stronger this pull becomes. In normal stars, this pressure is balanced by heat and energy produced by nuclear fusion. In white dwarfs, fusion has already ended, so a different type of force must resist gravity. That opposing force comes from quantum pressure generated by confined particles. As matter is crushed to extreme density, electrons are forced into minimal space. At this scale, the rules of quantum physics dominate. These rules prevent particles from occupying the same exact state. This creates a firm resistance to further compression. The result is a permanent balance between inward pull and outward resistance. A simple everyday comparison is a spring inside a press. When weak pressure is applied, the spring compresses slightly. As pressure increases, the spring becomes harder to compress. Even if the machine continues to push, the spring provides increasing resistance. A white dwarf behaves in a similar way, but the spring is built from the quantum behavior of matter itself. The internal structure created by this struggle is extremely stable. The star no longer expands or contracts significantly. It maintains a constant size for billions of years. This stability is not a sign of inactivity. It is the result of two natural laws constantly pushing against each other. The historical understanding of this balance developed when astronomers realized that classical physics could not explain the measured masses and sizes of white dwarfs. Calculations showed that without a new type of pressure, these stars should collapse completely. The inclusion of quantum mechanics provided the missing explanation. On a cosmic scale, this ongoing internal fight represents how the universe enforces limits. Even under extreme gravity, matter is not infinitely compressible. The structure of white dwarfs stands as a natural example of how microscopic laws control the largest objects in space.
White dwarfs do not cool quickly. Their cooling is one of the slowest natural processes known in astrophysics. This happens because of their extreme density and the way heat moves through their internal structure. After nuclear fusion stops, the star is left with a large amount of stored thermal energy. Heat inside the star can only escape by slowly moving from the core to the surface
and then into space. The packed structure of matter makes this process extremely inefficient. Energy moves through the star at a slow, controlled rate. In simple terms, this cooling behavior can be understood by thinking about insulation. Thin materials allow heat to escape quickly. Thick, dense materials slow the loss of heat. A white dwarf is made of matter so tightly packed that it behaves like the ultimate natural insulator. This causes the cooling process to stretch over billions and trillions of years. A useful everyday example is a large block of ice stored inside a cooler. A small ice cube melts quickly in warm air. A massive block of ice inside an insulated box takes much longer to melt. Even without adding new cold, the dense mass holds its temperature much longer than expected. White dwarfs follow this principle, but with heat escaping instead of cold melting. Natural changes linked to this slow cooling include a gradual dimming over time. The surface temperature decreases step by step. The color of the light shifts from white to yellow, then red, and eventually into invisible wavelengths. The object does not vanish. It becomes harder to detect. Historically, astronomers confirmed this slow cooling by studying white dwarfs inside star clusters of known ages. Older clusters contained cooler and dimmer white dwarfs. Younger clusters showed brighter ones. This predictable pattern allowed scientists to build accurate models of stellar cooling. At the scale of the universe, this slow release of heat means white dwarfs outlast most other luminous objects. Their cooling timeline stretches far beyond the normal active lifetime of stars, making them long-term markers of time in cosmic history. White dwarfs change size as they evolve, but they do not vanish. Their shrinking is controlled by how matter behaves under extreme gravity and quantum rules, rather than by burning or evaporation. As a white dwarf cools, it loses thermal energy. When heat decreases, the internal motion of particles slows. This causes the star to contract slightly. The contraction is not dramatic or sudden. It happens gradually over immense periods of time. The structure remains stable because a powerful internal pressure continues to resist full collapse. This supporting force comes from tightly packed electrons. Even as temperature drops, the electrons maintain a rigid resistance to further compression. This means that cooling leads to a denser and slightly smaller object, but not a disappearing one. The star approaches a stable final structure instead of breaking apart. A useful everyday comparison is a hot metal ball compared to a cold one. When metal is heated, it expands slightly. When it cools, it contracts. The metal does not vanish. It simply becomes more compact. A white dwarf follows the same physical behavior, but at far higher densities and pressures. Natural phenomena linked to this shrinkage include an increase in surface gravity. As the radius becomes smaller, the gravitational pull of the surface becomes stronger. Despite this, the star remains stable because the internal supporting pressure keeps pace with the increasing gravity. Historically, this behavior was confirmed when astronomers measured both the mass and size of many white dwarfs. They found that smaller white dwarfs could contain more mass than larger ones. This unusual relationship could only be explained by quantum mechanical support inside the star. At the scale of the universe, this process means that white dwarfs move toward an extremely compact, stable state known as a black dwarf. This final stage takes far longer than the current age of the universe. The star does not disappear. It simply becomes darker and colder while continuing to exist as a dense, silent remnant. White dwarfs are not only remnants of dead stars, they function as natural timekeepers for scientists who study the history of the galaxy. Their predictable cooling behavior allows astronomers to estimate how old groups of stars are. The basic structure of this method relies on temperature and brightness. When a white dwarf is first formed, it is very hot and bright. As time passes, it slowly loses heat and becomes dimmer. By measuring how bright and cool these stars are, scientists can calculate how long they have been cooling. This process can be compared to observing a cup of hot tea left on a table. A freshly poured cup is very hot. After 10 minutes, it becomes warm. After an hour, it approaches room temperature. If the cooling rate is known, it becomes possible to estimate how long the cup has been sitting there. White dwarfs work in the same way, but their cooling happens across billions of years instead of minutes. Natural structures involved in this process include star clusters. These are groups of stars that formed at roughly the same time. When scientists analyze white dwarfs inside these clusters, they gain a consistent reference point. The faintest and coolest white dwarfs indicate the minimum age of the cluster. The historical development of this technique began in the mid-20th century when astronomers realized that traditional methods of dating stars were limited. White dwarfs offered a more stable and predictable clock because their energy source was simple cooling rather than complex fusion processes. This discovery helped refine models of how the Milky Way formed and evolved. By studying the cooling stages of white dwarfs, scientists built a timeline of star formation across different regions of the galaxy. At the cosmic scale, white dwarfs extend beyond the role of ordinary stars. They preserve a slow, measurable record of time itself. Their fading light serves as a stable reference system for understanding how long stars, clusters, and galaxies have existed. White dwarfs provide a clear preview of what will eventually happen to stars like the Sun. Their structure shows the final stable state that medium-sized stars reach after using up their nuclear fuel. The Sun currently produces energy through nuclear fusion. Hydrogen atoms are pressed together to form helium, releasing heat and light. This process maintains a balance between outward pressure and inward gravity. When the hydrogen fuel in the core is exhausted, that balance changes. Fusion slows, and the star begins to transform. A star like the Sun will expand into a red giant phase. During this stage, the outer layers drift into space. What remains at the center is a dense, hot core. This core becomes a white dwarf. It no longer produces energy, but retains stored heat. A familiar everyday comparison is a campfire that has stopped burning. Flames disappear when the wood is consumed. What remains are hot embers that continue to give off warmth long after active burning ends. The sun will follow a similar path, ending not in flames, but as a slowly cooling stellar ember. Natural structures involved in this transformation include planetary nebulae. These are glowing shells of gas that drift away from the dying star. The white dwarf stays behind as the compact center. These nebulae are often observed in deep space images and confirm this process. The historical understanding of the sun's future became clearer when astronomers studied white dwarfs and connected their mass and composition to stars similar to the Sunday. This helped scientists confirm that typical stars do not explode as supernovae, but fade quietly into dense remnants. On the scale of the galaxy, this process is extremely common. Most stars in the Milky Way will follow this same path. White dwarfs therefore represent the standard ending for the majority of stars, including the one at the center of the solar system. White dwarfs serve as natural laboratories where the most extreme forms of physics can be observed without the need for artificial equipment. Their internal conditions cannot be recreated on Earth, making them valuable for testing how matter behaves under extraordinary pressure and density. The structure of a white dwarf allows atoms to exist in a state that does not naturally appear in normal environments. Matter is compressed so tightly that electrons dominate the behavior of the entire star. This makes white dwarfs ideal objects for studying quantum effects on microscopic scales, where very small particles control the structure of a very large object. In everyday life, laboratories rely on controlled environments to test materials. A pressure cooker, for example, increases internal pressure to change how water boils and how quickly food cooks. Even this sealed metal device represents only a tiny fraction of the pressure found inside a white dwarf. The star itself acts like a permanent, naturally occurring pressure chamber. Natural phenomena observed in these stars include predictable gravitational effects and stable surface conditions. Astronomers can measure how light bends and shifts when leaving the surface of a white dwarf. These measurements confirm theoretical predictions from both relativity and quantum physics. Historically, white dwarfs helped bridge the gap between classical and modern physics. Early observations showed that traditional gravitational theories could not explain their small size and large mass. This forced scientists to refine their models of matter and energy, leading to critical developments in quantum mechanics. On a cosmic scale, white dwarfs provide insight into the limits of material strength. They show how atoms behave when pushed far beyond normal limits. These stars allow scientists to test theories of dense matter without building machines, using the universe itself as a controlled experimental environment. Their continued existence gives long-term stability to these natural experiments, allowing measurements to be repeated across decades without significant structural change. Conditions inside a white dwarf represent extremes that current human technology cannot reproduce. The limitations come from pressure, temperature, and density that exceed the design capacity of any artificial system on Earth. At the core of a white dwarf, matter is compressed so tightly that a single teaspoon of material would weigh several tons. The pressure is so intense that atoms lose most of their empty space. Electrons, dominate the structure of matter. No laboratory device is capable of generating or containing this level of gravitational and quantum force at the same time. A familiar everyday comparison can be found in industrial machines such as hydraulic presses. These machines can crush metal and shape hard materials. Even the most powerful versions of these presses operate at pressures far lower than those naturally found inside a white dwarf. Human-made systems rely on metal walls and rigid frames, which would fail instantly under stellar-level pressure. Natural phenomena connected to these extreme conditions include gravitational redshift. Light escaping from the surface of a white dwarf loses energy and shifts toward red wavelengths due to the strong gravity. Scientists measure these shifts using telescopes, not machines, because no terrestrial device can safely reproduce the same effect. The historical development of this understanding came as scientists compared theoretical models with observational data. As measurements improved, it became clear that simple physical analogs on Earth could not match what was occurring inside these stars. This reinforced the need to use astrophysical observations instead of laboratory simulations. On a universal scale, white dwarfs serve as unreachable reference points. They define the upper limits of what natural pressure and density can accomplish without collapsing into even more compact objects. These stars demonstrate a boundary that modern engineering cannot cross. The study of these natural extremes continues through observational science, allowing humans to learn from environments that cannot be physically recreated or safely approached. Although white dwarfs are extremely distant from Earth, their existence has measurable connections to life and the development of human knowledge. These effects are not dramatic or immediate, but they are real and scientifically traceable. White dwarfs influence their surroundings through gravity and radiation. Their gravitational fields affect nearby objects, including gas clouds and companion stars in binary systems. In some cases, their stable light output provides reference points for astronomical measurements. These steady signals help calibrate telescopes and improve the accuracy of distance measurements across the galaxy. A simple everyday comparison can be found in the use of lighthouses. A lighthouse does not interact directly with ships physically. It provides a fixed, reliable point of light that helps navigation. White dwarfs act in a similar way on a much larger scale. Their predictable signals allow scientists to map the structure of space with greater precision. Natural phenomena tied to these stars include cosmic chemical recycling. Earlier generations of stars created heavy elements. White dwarfs often sit inside clouds of material that will eventually collapse to form new stars and planetary systems. This chain of events means that the matter that once formed dying stars contributes to the raw materials that later become planets. The historical role of white dwarfs in human civilization comes through their contribution to scientific frameworks. The study of these stars helped confirm quantum mechanics and improve understanding of gravity. These discoveries influenced technologies used in electronics, medical imaging, and communications. At the scale of Earth, white dwarfs do not threaten life. Their influence is indirect and long-term. They shape knowledge rather than environment. Their role is to quietly support the scientific models that humans use to understand where the solar system sits within a larger galactic structure. On a universal scale, white dwarfs act as stable background structures. They influence how galaxies evolve without disrupting local planetary systems, allowing life to develop without direct interference. In the far future of the universe, most familiar sources of light will have vanished. Massive stars burn quickly and disappear. Medium-sized stars fade into remnants. What remains active for the longest time are white dwarfs. The structure of these objects allows them to act as long-term light sources. They do not produce new energy, but they release stored heat so slowly that they continue to glow faintly long after other stars have stopped shining. This makes them the final visible embers of stellar activity. A useful everyday comparison is a campfire compared to glowing charcoal. Flames rise high and vanish quickly when the fuel runs out. The charcoal remains hot and glowing for much longer, even without flames. White dwarfs behave like cosmic charcoal, maintaining faint light while brighter stars have already disappeared. Natural processes surrounding this stage include the gradual darkening of galaxies. As fewer new stars are born and old stars disappear, white dwarfs become the main remaining visible objects. Their dim light dominates what little illumination is left in deep space. Historical models of cosmic evolution predicted this outcome once astronomers understood stellar life cycles. By comparing star remnants and cooling rates, scientists were able to model a future where white dwarfs outlast most other luminous structures. At the scale of the universe, this stage represents a transition from active, bright galaxies to a quiet, dark cosmos. White dwarfs serve as the final light sources, marking the last visible chapter of stellar energy. Even in this distant future, these stars remain stable structures. Their role changes from active participants in star systems to silent reference points of what once was a luminous universe. As the universe ages, heat slowly spreads out and becomes less available for doing work. This process is known as heat death. It describes a future state where temperature differences fade and energy becomes evenly distributed. In this stage, white dwarfs continue to play a role because they cool at an extremely slow rate. Even when other stars have disappeared, these objects still store small amounts of usable thermal energy. Over very long periods, even that stored heat is gradually released into space. A familiar everyday comparison is a warm room after the heater has been turned off. At first, the room feels warm. Over time, the warmth spreads and the air temperature slowly matches the colder outside environment. No new heat is created. The existing energy simply spreads until no usable difference remains. The universe follows the same principle on a much larger scale. The structure of white dwarfs makes this process visible to scientists. Their predictable cooling rates allow astronomers to model how energy will behave in the far future. Each stage of cooling represents a step toward thermal balance. Historically, the concept of universal heat loss developed from the study of thermodynamics. When astronomers combined these laws with observations of long-living stars, they gained a clearer picture of how the universe ages. Natural phenomena tied to this future include the gradual disappearance of large temperature gradients. Without active stars forming, galaxies become darker and colder. All matter moves toward a stable, low-energy state. On a cosmic scale, this stage represents a universe where structured motion slowly fades. White dwarfs act as some of the last objects to release stored heat, extending the final timeline of energy loss across unimaginable spans of time. Some objects in the universe behave in ways that appear close to immortality, even though the universe itself is not infinite in usable energy. White dwarfs represent the clearest example of this behavior. These stars do not create new energy after their main life ends. Instead, their unusual structure allows them to persist for time scales far beyond the active lives of typical stars. Their stability comes from quantum pressure rather than heat, making them resistant to collapse even when cold. A simple, everyday comparison can be seen in a sealed vacuum bottle. Hot liquid cools slowly when insulated. A perfect vacuum container can preserve temperature differences far longer than an open cup. A white dwarf behaves like a nearly perfect natural insulation system, maintaining its structure long after all internal heat has faded. The internal composition of these stars supports this longevity. Their atomic structure is locked in place by extreme density. There is no fuel to burn, and no easy pathway for collapse unless external mass is added. This makes their existence appear almost permanent on human and stellar timescales. Historically, the idea of long-lasting stellar remnants was developed when astronomers realized that these stars could not collapse further without exceeding known physical limits. This forced a shift in how scientists understood the concept of stellar death. Natural cosmic consequences of this stability include the slow fading of structure in galaxies. As active stars disappear, white dwarfs remain as isolated, cold masses that preserve the last organized structures of matter. On the universal scale, these objects represent the concept of endurance in a decaying system. They are not truly immortal, but they approach that idea more closely than almost any other known physical structure in the cosmos. The end of a star is often imagined as a clean and final event. White dwarfs show that this idea is inaccurate. Stellar death is not a sudden disappearance, but a slow transformation into a long-lasting physical state. When a medium-sized star finishes burning its nuclear fuel, it does not vanish. The outer layers drift away into space. The core compresses into a white dwarf. This process leaves behind a stable object that continues to exist long after active energy production has stopped. A simple, everyday comparison can be seen in the cooling of lava. When volcanic lava stops flowing, it does not disappear. It hardens into rock. The energy of motion ends, but the material remains. A white dwarf is the hardened core of a star, remaining after the active phase ends. Natural phenomena linked to this incomplete ending include planetary nebulae. These glowing shells of gas expand away from the core of the dying star. The core does not follow them. It stays behind as the dense, compact remnant. This shows that death in astrophysical systems often means separation and transformation rather than destruction. Historically, this understanding developed when astronomers began to carefully track star remnants. Early theories predicted complete collapse or explosive endings for most stars. Observations of stable white dwarfs required a new model of how stars end their lives. On a galactic scale, this slow ending changes how matter moves through the universe. Elements created inside stars are not destroyed. They are recycled into gas clouds that later form new stars and planets. The white dwarf remains as a marker of this previous cycle. At the scale of the universe, the death of stars appears less like an ending and more like a long-term restructuring of matter. White dwarfs demonstrate that cosmic endings are gradual, persistent, and structured rather than sudden and empty. White dwarfs reveal how the universe approaches emptiness without ever becoming truly empty. Their existence provides a physical reference point for understanding nothingness as a gradual process rather than an instant state. The structure of a white dwarf is based on matter reaching its most stable, compressed form without falling into total collapse. This creates an object that is no longer active, but never truly absent. It remains in space as a dense, quiet presence. A useful everyday comparison is a room after furniture has been removed. The room may feel empty, but air remains, walls remain, the space still exists. Emptiness is experienced, but physical structure continues. White dwarfs represent this same condition on a cosmic level. They appear lifeless, but they still occupy space and maintain form. Natural phenomena tied to this stage include the future absence of star formation. As gas clouds are used up or spread too thin, fewer new stars are born. White dwarfs remain as leftover structure in a universe trending toward simplicity and low energy. Historically, the idea that nothingness could be approached but never fully achieved developed through thermodynamics and cosmology. Researchers realized that energy does not vanish, it spreads. Matter does not disappear, it changes form. White dwarfs demonstrate this principle in the most extreme, tangible way. On a universal scale, these objects serve as physical reminders that the universe does not end in sudden void. It transitions toward uniformity. The fear of nothingness is replaced by the reality of persistence in a quieter, colder form. In this framework, white dwarfs become symbols of how existence fades in structure rather than disappearing entirely. They remain as proof that physical presence can survive, even when all active processes have ended.